Hello everyone. Welcome to the course Principles and Applications of Mechatronic Systems. I'm your instructor, Jiang Xinjia. Today we'll study Chapter 2, Fundamentals of Automatic Control, Application of Automatic Control Systems 2. Automatic control systems are widely integrated into various sectors of modern society, transforming production and lifestyle patterns, and serving as a key driver for technological and industrial advancement. So, what role do automatic control systems actually play in real-world applications? Let's delve into their practical applications and effective application methods. 1. Selection of control parameters. In system design, selecting the control parameters according to process requirements is crucial. The principles include choosing key parameters that directly determine output or quality and can be measured directly. If direct measurement is not possible, choosing indirect parameters that have a single-valued functional relationship with the direct ones, ensuring high sensitivity of the parameters, and considering both process rationality and the current state of instrument manufacturing. 2. Selection of manipulated variables. In an automatic control system, manipulated variables counteract disturbances that affect the controlled variables, typically in the form of medium flow rates. Once the controlled variables are identified, select from the controllable inputs those that significantly affect the system and have good controllability as manipulated variables. Others are considered disturbances. 3. Selection of actuators. In electromechanical control systems, actuators are mainly various types of motors, which can be categorized into conventional, servo, and special-purpose motors according to their applications. After determining the controlled variables, the influencing factors must be analyzed based on the process. Motors used for position control include stepper motors, DC servo motors, and brushless DC servo motors. 4. Selection of measuring instruments. Measuring instruments and transmitters must reliably, accurately, and quickly perform signal conversion. To achieve this, consider whether the instrument can operate reliably under field conditions over the long term, whether measurement errors fall within the process's allowable range, and whether the measurement signal's dynamic response is fast enough. 5. Selection of controllers. Controllers are the core of a control system. Their selection involves choosing the appropriate control law and determining whether to use direct or reverse action. The control law should be selected based on the characteristics of the controlled object to meet process requirements. The action mode, direct or reverse, should be chosen to form a negative feedback loop, ensuring system stability. 1. Selection of controller control law. A controller's control law refers to how its output signal U varies over time with the input signal E. The basic control laws include on-off, proportional, integral, and derivative control. In engineering practice, the most widely used laws are proportional, integral, and derivative control, collectively referred to as PID control. PID control is favored for its simple principle, ease of use, strong robustness, and broad adaptability. 2. Selection of direct or reverse action for controllers. It is necessary to consider that the product of the gain coefficients of the controller, actuator, controlled object, and measuring transmitter, denoted Kc, Kv, Ko, Km, must be positive. Given the signs of the gain coefficients for the object, control valve, and measuring transmitter, the controller's action, direct or reverse, can be determined. Gain sign determination. The relationship between input and output changes determines the sign of the gain coefficient. For example, in order to form a negative feedback loop for stable operation, we require Kc times Kv times Ko times Km is greater than 0. The gain signs of all components must be coordinated to ensure the control variable returns to the set point. 6. System operation and commissioning. Each part of the automatic control system is designed according to process requirements. After selecting instruments, installing and wiring them correctly, and ensuring all circuits are in order, and instruments meet accuracy requirements and function normally, commissioning can begin. Commissioning includes system startup and controller parameter tuning. 1. Startup of control systems. For single-loop control system, once designed, instrument selection, installation, and calibration are complete, or after a full shutdown and overhaul, the process of switching from manual to automatic control is called system startup. This is achieved by switching the controller from manual to automatic mode, and the transition must be disturbance-free. Preparations for manual to automatic switching include becoming familiar with the production process, understanding the control scheme, thoroughly inspecting all process measuring and control instruments, and conducting joint instrument loop testing. Steps for system startup: putting the measurement system into operation, performing manual remote control of the control valve, and switching the controller from manual to automatic operation. When switching from automatic to manual operation, first switch to manual remote control, then proceed to manual operation. 2. Engineering tuning of controller parameters. The goal of controller tuning is to determine appropriate values for the proportional band delta, integral time Ti, and derivative time Td of a PID controller based on the characteristics of the control process. In simple process control systems, the primary tuning criterion is the system's transient response attenuation ratio psi equals 0.75 to 0.9, while also considering steady-state error, maximum dynamic deviation, overshoot, and transition time to ensure stability margins. Tuning involves adjusting controller parameters to match the characteristics of a control object, thereby improving the system's dynamic and static performance for optimal control. Tuning methods include theoretical calculation tuning method and engineering tuning method. Ultimate gain method Ziegler, Nichols method: first set the controller type, then vary the proportional band to find the ultimate value and oscillation period, and calculate controller parameters using formulas. Field tuning method sets parameters empirically, applies disturbances, observes the response curve, and adjusts trial and error until the control quality meets standards. That concludes this lesson. Thank you for listening. See you next time.